Okay, so let's start your ISS journey uh, through the topic linear model. So, I think you all have heard the term a response variable and covariate or predictor variable. Covariate is the cause and the response is the effect. For example, rainfall is the cause and the output yield of paddy is the effect. The statistical plan from ancient age is to predict the response based on a covariate. That's a very basic need of the subject statistics. For this reason, this subject is so well celebrated throughout the world. Okay, but how this prediction can be done? That's another issue. This prediction work can be done loosely based on three statistical models. The first model is called the regression model. The second model we call Anova model, and the third model we call an Anokova model. Now the point is, when should we use a regression model? When should we use an Anova model? And when should we use an Anokova model? You have to understand this context because at the end of the day, a correct model matters the most. A correct prediction matters the most. And for a correct, accurate prediction, choosing the right model is very important. So you have to understand the context in which you should use a regression model, you should use Anova model, or you should use Anokova model. Now let's discuss about the context. If your response variable is continuous, and your covariate is also a continuous variable, then definitely you can opt for regression modeling. Suppose, for example, you have 50 students for whom height and weight are given. Obviously, you can predict their weight based on their height. So weight is the response and height is the covariate. And weight and height, they both are continuous in nature. So you can build up a regression model and do the prediction activity. Now you may use multiple types of regression equation, like you may use a linear regression, or you may use a polynomial regression, or may use in some other type of regression model. Okay, but you can only use a regression model whenever the response is continuous and the covariate is also continuous. In this context, regression is appropriate. Now, what is the context in which you can use ANOVA? Let's see. The response variable is continuous, but the covariate you're using is categorical variable. Then ANOVA model is important. For example, why is your score in ISS? Okay, and the covariate is the teacher you have chosen. Suppose there are 3 teachers who give tuition for ISS. Okay, so naturally this covariate is categorical. Maybe it's an ordinal or nominal. Ordinal because some teacher is superior and some are not. You know from your BSc days that some teachers are great and some are not. Anyways, that's not the issue, but the issue is if the response is your score, which is definitely a continuous variable, and the predictor you are using is categorical predictor, then definitely you cannot use the regression equation. In this context, you have to use ANOVA. Okay. Now ANOVA model can be multiple, like one-way ANOVA, two-way ANOVA, ANOVA fixed effect layout, ANOVA random effects model, ANOVA mixed effect model, etc. There are multiple kinds of ANOVA model, right? Just like regression model, there are multiple kind of stuff. But contextually, you can only use regression when response and covariate both are continuous in nature. But you can use ANOVA when the response is continuous and the covariate is categorical. Now, when you can use ANOVA? ANOVA means analysis of covariance. Here the response is continuous. But the predictor, they can be categorical and continuous both. For example, the response is your ISS score. One predictor is your choice of teacher. Definitely choice of teacher is categorical in nature. We know very well that only a teacher cannot fetch you all the success. You need something more. That is your perseverance. That is your effort. That is time of study you have to invest. This is one more very, very important feature. A very, very important predictor. While you are predicting your ISS marks. So teacher, it's a categorical covariate. Your time of study is definitely a continuous covariate. So the response is dependent upon continuous predictor as well as categorical predictor. So it's a blended kind of a model, a blend between regression model and ANOVA model. Such a model is called an ANOVA model. Okay, in your undergrad days, you have analyzed regression model, you have analyzed your ANOVA model, and you have analyzed your analysis of covariance model. Now, what if I want to unify all these 3 models into a specified model? I think you all have heard about Stephen Hawking, right? The famous scientist. He had a dream. Do you know what is a dream? His dream was theory for everything. Yeah. He wanted to make some physical law which can explain all the physical activities that are being happening in this universe by one single law. But he couldn't achieve it completely. But in statistics, Gauss and Markov, they did something like that. They named a model called linear model or Gauss-Markov linear model. This linear model unifies all the three models that we have discussed: the regression model, the Anova model, and the Anova model. They have given a very generalized structure. One subpart of that structure would give you the regression model, one subpart of that structure would give you the Anova model, and one subpart of the structure would give you the Anova model. That model is called Gauss-Markov linear model. That's your first chapter. Okay. Now, what is a linear model? That's a query. Let's develop a linear model. So once again, you have the response variable y, and if you have some covariates x. I'm not mentioning the nature of the covariate. Okay, I won't mention the nature of the covariate. Just I'm putting up the model like this. That's your first response. The response is modeled by this structure: beta 1 x11, beta 2 x12, beta p x1p plus e1. Okay, x11, x12, x1p, they are the covariate values, and e1, you know very well that any statistical model contains some error quantity, so e1 is that error. Then the second response, y2, beta 1 x21 plus beta 2 x22 plus beta p x2p plus e2. In this way, the nth response yn, that's beta 1 xn1 plus beta 2 xn2. In this way, beta p xnp plus en. Now, this is quite a complicated structure because you have n responses and you have n equations. You have to unify this equation. How can you unify this? You have to use linear algebraical notations. How? First, take all the responses inside one vector like this. Now you have this pretty large structure. Just use this matrix thing: x11, x12, x1p, x21, x22, x2p. In this way, xn1, xn2, xnp. Plus, put up all the error quantity inside one vector like e1, e2, en. Sorry, a bit of small mistake. into a vector beta 1, beta 2, beta p, then add the error term inside one vector. Now
beta n,
beta p, not beta n.
sorry,
Now justification of the structure. If you are skeptic, then you have to justify yourself why the previous thing and this thing, they are the same. Why? See, let's multiply. The first line would be beta 1 x11 plus beta 2 x12 plus beta p x1p plus this error e1. That would represent the first row, that is y1. Now check. Y1 is beta 1 x11 plus beta 2 x12 plus beta p x1p plus e1. Now the second row, beta 1 x21 plus beta 2 x22 plus beta p x2p plus e2 equals to y2. Let's check. Beta 1 x21 plus beta 2 x22 plus beta p x2p plus e2. In this way, the nth row, yn, beta 1 xn1 plus beta 2 xn2 plus beta p xnp plus en. Let's check this. So this whole complete structure can be represented in just one line using some very basic vector and matrix notation. The subject linear algebra was developed just for this cause, to represent complex equation in a simplified manner like this. Okay, so this is one vector. Name this vector as y curl. That's a matrix. Name this matrix as capital X. Then with X another vector is multiplied. Name it beta curl. And in the end you have one more vector like this. Just name it E curl. Now just tell me, what is the order of y curl, what is the order of x, what is the order of beta curl, and what is the order of E curl? Tell me.
n cross 1, x over n cross p,
N cross 1, x is n cross p obviously, n rows and p
p cross
columns,
1,
p cross 1,
n cross 1.
perfect. This is your Gauss-Markov linear model. Gauss-Markov linear model. But this linear model needs some assumptions. What are the assumptions? The first assumption is all the error components are independent. E1, E2, En, they are independent. That's the first assumption. Number 2 assumption. The error components are homoscedastic. That means each and every error component has equal variance sigma square. All the error components
No, all EIs are homoscedastic.
I'm having a bit trouble with the board pen. So that's the second assumption, that all the error components are homoscedastic. Now, in short, you can say that this vector E curl follows an invariant normal with mean vector null curl and dispersion matrix sigma square IN. Okay, so these are the assumptions of Gauss-Markov linear model. Very, very essential assumption. If one of the assumptions gets violated, then we cannot use this Gauss-Markov linear model. I think you'll face a few questions regarding assumption in your mainframe exam. Okay. Now, the most important query of today's class. We have already said that this Gauss-Markov model is actually a theory for everything, because this model can be used as a regression model, this model can be used as a Anova model, and this model can be used as an Anova model. Now, how this can be decided, whether this model is a regression model, or it's an Anova model, or it is an Anova model? Everything is decided by this matrix X. It's a very, very pivotal matrix. This matrix X is called the design matrix. So the most pivotal question is that how the nature of this design matrix decides whether a linear model is actually a regression model, or an Anova model, or an Anokova model. Design matrix, the name, is actually from designing the model. Designing the model as regression if all the elements of X can take any value. Like any continuous value, 2.3, 0, 4, 5, that is that these elements, they can take any value. Okay, then the linear model can be regarded as a regression model. But if the elements are binary 0 and 1, then this linear model would be called an Anova model. And if some of the elements are binary like 0, 1, 0, 1, and if some of the elements are continuous, then we can say that the linear model is giving me an Anokova model. So that's the very basic framework of linear model theory. And you have to remember one thing, These assumptions are very important. If any one of the assumptions fails, then the entire theory would just be erupted. Okay, you have to modify the theory completely. So in the next day would start, I think Wednesday is a good day for that. How to estimate the model parameters. Now can you tell me who are the model parameters here? This beta 1, beta 2, beta p, they are called the model parameters. This vector is called vector of model parameters, this beta curl. So in the next class we'll discuss how this beta curl can be estimated using method of least square. Then we'll solve a few problems of Loom and other things that would be helpful in your course. So next class, Wednesday, 11:30.